Hello students, I am Azizi, Professor Electronics. In our previous session, we have written an assembly language program for flip-flop, and we have observed the set reset flip-flop on hardware, as well as we have developed the software using assembly language. First, we'll observe the previous simulation of our program. Then we'll write a new program, that is the counter program. If we'll press the switch 1, then the counter will be incremented. So let's start our today's session. Here we can find we have developed our microcontroller circuit using Proteus software, and we are using AT89C51 microcontroller. And in previous session we have developed a program for the flip-flop, and now we'll run the simulation and we'll check our previous program. Here we can check the LED 1 is on, that is D1 is on. If we'll press switch 2, then LED 2 is on and LED 1 is off. And if we'll press the switch 1, LED 1 is on and LED 2 is off. We call this logic as set reset flip-flop, and here we have switch 1 and switch 2. We'll call the switch 1 as set and we'll call the switch 2 as reset. As the switch 1 set the status of D1 as high and reset the status of D2 as low, and the switch 2 will set the status of D2 and reset the status of D1. So we'll call this program as set and reset flip-flop program. And now we'll develop another program to run a counter on port 0. And in our previous session we have learned that what is counter, and we had developed a program to run the counter on port 1. Now we will develop a program to run on port 0. Here we can find decimal and binary number counters. Here we can see the decimal number counter counts in decimal, while the binary counter counts in binary number system, and we will develop a program that will count in binary format on port 0. So let's start writing our program. In this program we will use switch 1 as increment switch. If we'll press switch 1, the port 0 will be incremented by 1 and it will count from 0 to 255. Because the length of the port 0 is 8-bit, so the number can go from the 0 to 255. So let's start writing our manual counter program. Before writing our program, we will discuss two things. In our program, we will use a switch to increment the counter, and here we have a switch which is connected on port 2.0. and it is a switch 1, and we'll call it increment switch. And this switch is active low. It means that by default the status of the switch will be high, and if we'll press the switch, the status will be 0, and if we'll release the switch, the status will again go high. So here when we will press the switch, we'll observe bouncings on falling edge and the switch will go low, and when we will release the switch, again we will observe bouncing and then it will go high. So we'll use a technique to filter out these high frequencies. We'll use a digital filter to filter out this frequency. Secondly, we will perform the increment action on rising and falling edge of the input 2.0, and here we have the falling edge and here we have the rising edge. So we will use the falling edge to increment our counter, and we will separate the falling edge using the software technique. And here on falling edge we will have a pulse like this, and on this pulse the counter will be incremented. So let's see how we can perform these two tasks, that is to filter out the bouncing frequency and to separate the falling edge from the switch. And here we have our previously written program, that is the flip-flop project. Now we'll write our new program. So first we'll go and close the project. New microvision project, and here we'll assign the name to our project, that is manual counter project, and here we have assigned the name to our project, that is manual counter project. OK, save. Now we'll select the microcontroller, that is 89C51, and here we have the microcontroller. OK, and we'll right click the target 1 option for target 1, and here we will assign the crystal oscillator frequency, that is 12 MHz in our case, 12.0, and we'll go to the output and we'll select create hex file. OK. Now to the source group 1, right click, add new item to group, source group 1, and here we'll select ASM and we'll assign the name manual counter. OK, add, and now we'll write the name of our project in comments, and now we'll write the variable assignments, and here we can find the general purpose RAM starting from 30H to 7FH, And in our program, we will use the first location, that is 30H, as counter reg, and here we'll assign the first variable, that is counter reg. And we'll assign the location, that is 30H, to this counter reg, and we will write EQU, and here we will write that is 30H. We can add more variables as and when required in our program. So here we will close this session, and now we will write the ports assignments, and we will assign a name, that is counter port to port 0. So here we will write that is counter port EQU port 0, and here we will close the session. In this program, we will use some flag bits. So here we will write the flag assignments, and here we will add the flags as and when required in our program. For now, we will leave this section empty, and now we will write the directives for the compiler, and here we will write originate, that is org, and here we will write 0000H, the reset vector for the microcontroller, and here we will write the first instruction, that is jump to initialization routine. So here we will write that is jump ini_r. You can assign any name to your initialization routine as per your convenience, but here I am using the name, that is inir, for initialization routine. Now we will originate the second address, and here we will write org, and we will write 0030H, and from the address, that is 30H, we will start writing our initialization routine, and here we will assign the label, that is inir, using colon, and here we will initialize the counter reg and counter port to 0. So we will write that is move counter port comma hash 00H, and we will write that is move counter reg comma hash 00H, and here we'll close the initialization routine session. We can initialize more variables here in initialization routine as and when required in our program. Now we'll write our main program, and here we'll write main routine main_r using colon, and here in main program we'll call two subroutines, that is increment routine and display routine. So we will write that is call inc_r, and here we'll add a comment, that is increment routine, and we'll call another routine, that is display routine. So we'll write that is call disp_r, and we will add a comment on this line, that is display routine, and after calling these two subroutines, our program will jump back to the main R label. So here we will write that is jump main_r, and here we'll close the session of our main program, and now we'll write the increment routine, and here we'll write that is incr using colon. So here in this increment routine, first we'll check the status of the switch 1, that is the increment switch. So first we'll define the variable for increment switch, and here we'll write the assignment for the switches, and here we'll assign the name which is connected on port 2.0 as increment switch. So here we'll write that is inc_sw, and we will use that is bit, and we will write that is port 2.0. And now in subroutine we'll check the status of the increment switch. If the switch will be pressed, then the status of port 2.0 will be low, and if the switch will be released, then the status of port 2.0 will be 1. So here we'll check the status of the switch by using command jump not bit. So here we'll write that is jump not bit, the increment switch. It means that jump to a location if the status of the respective bit is 0. So here we'll assign the label that is increment routine 0. So here we will write that is INC underscore R underscore 0. And if the switch is not pressed, then the status of the port 2.0 will be 1. In this case, our program will come to the next line. And on next line, we will write that if the switch is not pressed, just exit from the routine. So here we will write that is jump increment exit INC underscore EXT, and we will use this label to exit from the increment routine, and we'll write the subroutine that is increment exit at the end of increment routine. But here we have assigned the name to the subroutine, and now we'll write the increment routine 0, and here we'll write that is INC underscore R underscore 0 using colon. If the increment switch will be pressed, then our program will come to the increment routine 0. And here in this routine, we will filter out the debouncing frequency. For this, we will use a register that is debouncing register. So first we will define the variable that is debouncing register. And here we will add another variable that is db underscore reg EQU 31H, that is the second address of general purpose RAM, and we will initialize this variable in our initialization routine. So here in initialization routine, we will write that is move dbreg comma hash 00H, and now we'll use this variable that is dbreg as debouncing register. And here in this increment routine 0, we will check if the switch is pressed, then we will increment the debouncing register by 1. But first we will compare the value of the debouncing register with FFH, that is the maximum value for 8-bit, and which is equivalent to 255 in decimal number system, because the DB register is a RAM location and we cannot compare the RAM location with the direct number. So first we will move this register in accumulator, and then we will compare the accumulator with FFH. So here we will write that is move accumulator comma dbreg, and now we'll compare the value of accumulator with FFH, and here we'll use a new command that is compare jump not equal accumulator comma hash 255, that is the decimal number, comma. In this case, if the value is not equal to 255, our program will jump to a new subroutine and will assign the name to the subroutine that is dbreginc, and here we'll write debouncing register underscore inc. Here on this line, our program will check if the value of accumulator is not equal to 255, then the program will jump to the debouncing register increment routine. But if the value of debouncing register will be 255, then our program will come to the next line, and here we will write that is move dbreg comma hash 00H, and here we have initialized the debouncing register to 00H, and here we'll set a flag on next line that the switch is pressed for a certain interval of time, and here we'll write that is set bit debouncing flag dbflg. Here we have used a variable that is debouncing flag, and we'll define this flag in our flag assignments. Here we can check we have bit addressable locations starting from 20H to 2FH. We'll use the first location of 20H location as debouncing flag. So here we'll define that is db underscore flg, and we'll use bit, and here we'll write 00H. As we have defined a new variable that is debouncing flag, so we'll initialize this variable to 0 in our initialization routine. So here we'll write that is clear debouncing flag. So here we have cleared the status of debouncing flag, but here we have set the status of debouncing flag. It means that if we'll press the increment switch, for the time period, which is equals to 256 multiplied by the machine cycles required for compare jump not equal instruction, and we can check from the instruction reference. And here we can check the opcode, that is 85, compare jump not equal, accumulator, direct number, and jump to the offset. It requires 3 machine cycles, and we are using a 12 MHz crystal, and our machine cycle is 1 microsecond. It means that if we'll compare this number with 255, so the length of the delay will be 256 multiplied by 3 microseconds, and here we can calculate the length of the delay, that is 256 multiplied by 3 microseconds, which is equals to 0.768 milliseconds. If we'll press the switch for 0.768 milliseconds, then our program will consider this switch as a valid input. Otherwise, if we'll release the switch before 768 microseconds, then our program will not accept the input as valid input. And here we can check on this line, we have written an instruction, that is jump not bit, increment switch, increment routine 0. But if the switch is not pressed, or we will release the switch before 768 microsecond, then we have to initialize the dB register value to 0. So here we will write, that is move dB reg, comma hash 00h. In this case, our program will initialize the dB reg to 00. But if we press the switch, that is increment switch, for the duration that is greater than or equals to 768 microsecond, then our program will come on this line and it will set the flag, that is dB flag. And after setting this dB flag, our program will get exit from this routine. So here we will write, that is jump increment exit. And now we'll write the routine, that is dB register increment routine. So here we will write dB underscore reg underscore increment with colon, and here we will write just increment dB reg, and after incrementing dB reg, our program will get exit from the subroutine. So here we will write, that is jump increment exit. And if we'll press the switch, that is increment switch, for a longer duration, our program will continuously come to the increment routine 0. So here we will use an interlock, that is if the dB flag is set, then our program will no more check the increment switch. So here we will write, that is jump not bit dB flag, that is debouncing delay routine, and here we will write debouncing DLY underscore R, and we'll assign the name, that is debouncing delay routine, to the routine in which we are checking the status of increment switch. So here we will write debouncing underscore DLY underscore R using colon. On this line, we can check if the status of the debouncing flag is 0, then our program will jump to debouncing delay routine, and here it will check the status of the increment switch. But if the debouncing flag will be set after the duration of 768 microsecond, then our program will come to the next line, and here it will check if the increment switch is released or not. So here on next line, our program will check if jump not bit, that is increment switch, comma increment exit, and when the increment switch will be released, if the debouncing flag is set, then our program will come to the next line, and here on next line, our program will increment the counter reg, INC, and here we have the variable, that is counter reg, Control C, and we will paste it here, Control V, increment counter reg, and after incrementing the counter reg by 1, our program will reset the debouncing flag and get exit from the subroutine. So here we will write, that is clear debouncing flag and jump INC EXT, that is increment exit, and here at the end of increment routine we'll write the label, that is increment exit. So here we will write, that is INC EXT using colon, and here we will write return, and here we will close the session for increment routine. Here we have completed our first routine, that is increment routine, and now we'll write the display routine, which is very simple routine. So here we will write the display routine, and here we will write that is dispar using colon, and here we will move the value of counter reg to port 0. So here we will write that is move, and here we have assigned the name, that is counter port to port 0. So we'll copy this variable from here, Control C, and we'll paste it here, that is Control V, comma, counter reg, and we'll get exit from this display routine. So here we will write that is return, and we'll close the session for display routine here, and here we'll write the instruction, that is end for the compiler. It means that to compile the program till the end instruction, and here we'll write the instruction, that is end, and here we have completed our program. First we'll go through our program, then we'll compile the program, and we'll check the result of our program on Proteus simulator. So here we have written the name of our program, that is manual counter program, and here we have written the variable assignments, that is counter reg, and we have used the hardware address, that is 38, the first address of the general purpose RAM, and here we have used the second variable, that is debouncing register, and we have assigned the second address of the general purpose RAM to the debouncing register, and we have assigned the name, that is counter port to port 0, and we have used the first location of the bit addressable RAM, which is starting from 20H, and here we have used its first bit, that is 00H, and we have assigned the name, that is increment switch to port 2.0, as we have connected our first switch on port 2.0, and here we have returned the directives, that is originate the address 00H and jump to initialization routine, and we have started the initialization routine from 30H, and here we can find our initialization routine. We have initialized the counter port to 00H, which is the port 0, and we have initialized the counter reg to 00H here. We have moved the value, that is 00H to debouncing register, and here we have cleared the status of debouncing flag. It means that whenever we'll power up our circuit, all these variables will be initialized through initialization routine. Then a program will come into the main routine, and here we are calling just two routines, that is call increment routine, call display routine. And on the first line of increment routine, we are checking if the status of the debouncing flag is 0 or not. If the debouncing flag will be 0, as we have cleared the status of debouncing flag in initialization, then our program will jump to the db delay routine, and here we have the debouncing delay routine, and here we have written that if the status of the switch is low, then go to the increment routine 0. If the switch will be pressed, then our program will come to the increment routine 0, and here it will move the value of debouncing register to accumulator to compare it with 255, and here we have written an instruction, that is compare jump not equal accumulator with 255, go to the debouncing register increment, and then our program will jump to the debouncing register increment routine, and here it will increment in debouncing register and will get exit from the subroutine, and here we can check the label, that is increment exit is written on the next line of this instruction. So there is no need to use this instruction here, that is jump increment exit, because after incrementing debouncing register, our program will get exit through this return instruction. So we'll remove this instruction from here, delete. If we'll press the switch for the certain interval of time, that is 768 microsecond, then the value of the debouncing register will be equals to 255, and in this case our program will come to the next line, and it will reinitialize the value of debouncing register to 00H, and it will set the flag, that is debouncing flag, and it will jump to the label, that is increment exit, and will get returned from the subroutine. But if the debouncing flag will be set, then our program will come to the next line, and it will check if the increment switch is still pressed. It will go to increment exit, and it will get returned from the subroutine. But if the switch will be released, it will come to the next line, and it will increment the counter reg by 1 and clear the status of db flag and jump to the increment exit, and will get returned from the subroutine from this line, that is return. And here we have written the second subroutine, that is display R. Here we can find display R, dispar, and here we have written move the value of counter reg on counter port, which is port 0, and after moving the value of counter reg to port 0, our program will get written from this line, that is return. Now we'll compile our program and we'll check the result of our program on Proteus. First we'll save the project and we'll compile our program. Here we can check 0 error 0 warning. Now we'll download the hex file to the microcontroller and we'll check the result of our program. Now we'll download the new hex file to the microcontroller. And here we have the hex file, that is manual counter project. OK. And now we will run the simulation. Here we can find the value of port 0 is 0. If we'll press switch 1, here we can check the value is incremented by 1 and the LED 1 is on. If we'll press it second time, here we can check the value is now 2 and the second LED is on. If we'll press the switch 1 once again, the value will be 3. So let's check. And here we can find the value is 3. So if we'll press the switch many times like this, we can check, we can increment the counter manually, and the maximum value of the counter can go up to 255. As we know that the length of the port 0 is 8-bit, so we can count from 0 to maximum 255. So here we have completed our task for manual counter increment, and here I would like to give you a new assignment, that is to modify this program and add a decrement routine in this project and check your result on Proteus simulation. In next session, we will add a reset input to this program, that is if we will press the reset switch, the value of the counter will be 0, and we will learn some more assembly language techniques in our next session. Thanks for watching the assembly language programming course. We hope that you find this course very helpful to learn assembly language programming. If you feel that this course contributes and enhances your embedded system design knowledge, then go ahead and hit like, share and subscribe buttons, and do not forget to press bell icon to stay updated with every new upcoming video from Electroeducators as soon as it goes up. Electroeducators also offers technical consultancy in following fields. For assistance regarding technical problems, projects and any consultancy, feel free to reach out at our email address electroeducators@gmail.com. Okay, see you in next lecture.